In the third exercise for image fusion, we will look at CT-based brain spatial normalization, allowing us to use standardized brain atlas on our PET data based on the CT anatomy. This exercise will continue in the FUSIT tool, and we will use RAT4 from the Bruker PCI database. If desired, the PET and CT could be loaded using the hybrid workflow to check the co-registration. In this case, we will go straight into the spatial normalization. Open the FUSIT configuration in the lower left, where we can change the default matching mode from hybrid to deformable. Select only the CT image and open it. When a single image is selected, even when it's CT or MR, it will automatically be assigned as the input image. Since we're only interested in the brain, we can crop the image around the skull. To crop the input image as part of the workflow, we can expand the controls in the lower right corner, revealing the cropping dialog, where we can turn on the cropping checkbox, which reveals a yellow box for cropping on the image display. In this case, we can reduce the dimensions in the Z direction so that we enclose the skull, throwing away the unnecessary information from the rest of the body and the front of the head. When we proceed with the deformable matching workflow, first we will be asked to crop the image, so we can confirm. Then we're taken to the reference and matching page, where we will load a reference image. Built-in brain templates are available from the Brain Templates button to the right of the reference file dialog. In this case, to use the CT template, we will actually load it as auto-detect. In this case, for the exercise, the CT template is on the PMOD USB stick in the PMOD trial folder, PMOD data CT template, and within that folder we'll see the interfile pair header and image. Select the RAT CT template work in progress header and open. The field of view in the template image is deliberately limited to exclude information outside the brain. However, a misrotation of our input CT series is clear, so we can use the input reslicing controls on the right-hand taskbar to translate and rotate using the controls seen in earlier exercises, so that we can bring the individual CT more closely into alignment with the template. You can always use the fusion controls to assess that alignment. We don't expect to have a perfect rigid match because the template and the individual input are not the same subject. Check that the species is correctly identified as rat. Due to the cropping down to the skull only, the volume can fit into the detection parameters for mouse. So we switch to rat. We still have deformable matching set, and then we can proceed with the deformable matching using the Match Current Workflow button. After the calculations are complete, we're taken to the matching result page, where we can assess how well the spatial normalization has worked. A useful technique is to turn on contours for the brain template, allowing us to compare those to the input image. Contours can be turned on using the fusion controls below the main image controls. and to display only a contour for the reference image, we can select the B radio button. The contour itself can be adjusted by selecting the controls for the reference image and then the Contours tab, where the contour threshold can be adjusted using the slider. Now that we've displayed the contour for the reference image, we can adjust the fusion controls to show only our input image, and then we can use the cursor to explore the image and decide whether the contours of the skull for our input fall within the contours displayed for the template. In this case, the spatial normalization result is acceptable, so we can save the transformation to use on the PET data. On the right-hand side above the workflow buttons, we are able to save the transformation that transforms our individual CT data to match the template. We'll save the transformation to the database so that it can be easily retrieved. In this case, a name such as CT to the CT template is acceptable, and we can iterate the number for the number of times we run through the exercise. The transformation saved will now be applied to the PET data so that we can apply the Atlas VOIs to the PET data for analysis. In this case, we can return to the Load Input Images page of the workflow, where we can use Load Database to select the PET data. In this case, we select the FDG PET Whole Body series and load. Once again, we can crop the image around the brain and then proceed with the workflow. The crop checkbox remains active from the last part of the workflow. In this case, we can adjust the dimensions once again and center the box around the brain. Now we can proceed using the Deform Workflow button, accepting the crop. And then we move on to the reference and matching page. In this case, we will not calculate matching anymore, but we will use the green workflow button to proceed directly to the matching results subpage, where we can load the transformation we just saved. Again, on the right-hand side above the workflow buttons, we now have the option to load transformation. This opens the database containing the transformations saved for this exercise. We should select the transformation just saved and retrieve it. Once retrieved, the transformation is applied immediately, and we should see it applied to the PET data. Once again, we can use the Fusion slider to inspect the result, and we see quite clearly how the PET data fits within the contours of the skull from the template. Next, we can proceed through the workflow using the VOIs workflow button. And now, rather than using the VOI definition tools that we've seen so far, we will load predefined Atlas regions for the rat brain. First of all, for an easier display, I will turn off the contouring using the contour button below the Fusion controls. Next, I go to the Template VOI tab, bottom center of screen, where I can select the Atlas subtab, and then I should select the appropriate Atlas, in this case the PX rat from the Schiffer group. A preview of the VOIs for the brain atlas are shown in the image display, and these should be outlined onto the image to allow us to actually calculate the statistics. Below the selection for the atlas, we have the outline button. The VOIs themselves are organized in a tree structure, which can be expanded using the arrow below the VOI list. Here we see all of the available regions and that tree structure, and we could choose to only outline a subset. For this exercise, we'll outline everything, so I can continue with that by clicking on the outline button. Following outlining, we switch to the List VOI tab, where we can see that we have 58 standard Brain Atlas VOIs applied to our data. Do note that these Atlas VOIs are generalized. In this case, they may be slightly expanded compared to the brain data, but they allow you to work in a very reproducible way. These regions can be saved as usual, and the statistics can be calculated for use in your study. In this case, using selected statistics, we can calculate the average and standard deviation for all of these Brain Atlas VOIs. The statistics dialog appears as usual. We can select the statistic of interest on the right-hand side, and we see the list available for all of the brain regions.